Hello everybody. Here in this video today we are going to be doing guided examples with the double angle identities. So you definitely want to have out your notes from the lesson introduction for the double angles, and you're going to be referring to them. Additionally, anything that you have learned prior to this is your responsibility for knowing, and it's fair game. So we can have reference the fundamental identities. Maybe we could reference the angle sum or difference identities. By fundamental, I of course mean reciprocal, quotient, and Pythagorean, and anything of that sort. So what we'll do in this particular video is after each guided example, I will immediately tell you which one I want you to do on your own, which will be in the same category as that guided example, so that you can do the guided example with me, see your on your own example, and press pause on the video, work on that one, maybe rewind, look things over again, look at your notebook again, try that on your own example, and then once you're done with that, carry on, example 2, and then I'll give you the on your own number 2, etc. So let's get started. Here on the first example, we are given cosine of u is equal to -3/5. Now, every time I'm given a math fact, I like to kind of pause and address it, deal with it, so that I don't have to read the problem more than once. I'm not a big fan of rereading the problem 100 times. I feel like if you read the whole thing, sometimes you end up more confused than necessary. So if cosine of u is an angle, is equal to -3/5. -3 would represent, if it were a right triangle, the adjacent side, and 5 would represent the hypotenuse. So cos𝑢𝑥. Now we know from angles in standard position that we've been doing all year that -3/5, when cosine is negative, that could be in either quadrants 2 to the left or quadrant 3. So I've narrowed it down in my head to quadrants 2, and 3. So if I keep reading, I'll probably get some more information. So I'm not going to draw a picture yet because I don't know where it is specifically. With u, now this is, pay attention to how I read this. You should read it the same way. With u, the angle u, being between pi and 3pi/2. No one reads this pi less than u less than 3pi/2. That's silly. Don't do that. U is between those two bounds. Okay, that is on the low bound. Okay, lower bound, upper bound. So it's bounded between those two angles. Well, now I know which quadrant it's in, and I hope you know as well. That would mean it's in quadrant number 3. We use Roman numerals for our quadrants. So again, before I continue, I'm going to sketch out a bit of a picture. So quadrant 3 is the lower left quadrant. An angle in standard position would always require us to have the origin in sight. It also requires us to, more than likely, draw our reference triangle. So there's our reference triangle, and this would be our reference angle u. So it's not really angle u, it's just the one we refer to. We said that SOHCAHTOA, that this is adjacent, -3, over hypotenuse, 5. You also want to remember that the hypotenuse is never negative. So the negative sign in any of these ratios will always go with either adjacent or opposite, if not both, depending which trig function you're working with. And we tend to write our fractions with the negative on the numerator, but if it were, say, secant u instead of cosine, right? So this is just a little thought bubble. You're having a thought. Secant u, so this is the same. Secant of u would equal -5/3. I wrote the negative with the 5 because I wanted it in my numerator. That doesn't mean 5 is negative, okay? Keep that in mind. That's just a passing thought. Here we go. Now, I know it doesn't ask me to find the missing side of the triangle right now, but you're probably going to have to do that. This is a Pythagorean triple. You should know by heart how long that missing side is. And if not, you have to use Pythagorean theorem, which is, of course, a² + b² = c², such that c is always the hypotenuse. And obviously, you can only use it on a right triangle. and just make sure you're careful and don't make any silly mistakes. But I'm going to save time because I know it's a Pythagorean triple. It's a 3, 4, 5 triangle. And since I'm going down in the y direction, that has to be a -4. So now I have a good solid reference triangle. Find sine 2u. Sine of 2u. That doesn't mean we find the sine of u and double it. It just doesn't work that way. I'm sorry, okay? Another example of something that doesn't work that way, like, for instance, the square root of 4, right? The square root of 4 is equal to 2. Now, if I double that 4, square root of 8, is the square root of 8 4? Do I just double my answer? No. The square root of 8 is the same as square root of 2 times 2 times 2, which of course is 2 root 2. So you can't, there's no shortcut, all right? There's no shortcut. So we don't just double our answer of sine u. There's a process. And that was the whole point of the lesson intro. I gave you guys all a formula that we'll use. So you should be able to find that in your notes. 2 sine u cosine u. Whatever letter we're using for the angle, we're just consistent with that. Okay. That's 2 times whatever the sine of u is times whatever the cosine of u is. Now, if this u were to be replaced with an angle on the unit circle, then I would just evaluate it using the unit circle. It probably won't. That would be a little too easy because any angle that we would fill in for u, if I double it, it's still on the unit circle. There's no need. Like, we don't need to use this in that situation. Sine of u, we look at the picture. Sine is going to be, I'm just going to show work, opposite over hypotenuse, and cosine will be adjacent over hypotenuse. All right? Just showing some work. Equals 2 times opposite over hypotenuse will be -4 over 5. Adjacent over hypotenuse, that was also given to us, -3 over 5. 2 is really over a 1. 5 times 5, my only denominators I have to really worry about multiplying is 25. And then, careful with the signs, negative times negative is positive. 4 and 3 is 12 times 2, 24. Final answer. So could I have written sine 2u every step of the way? Absolutely. I'm just filling it in after the fact, sine 2u, so that my final answer is a full thought. And there we go. So I wrote down what guided example it was. I wrote down my directions. I drew a picture to help out. And I rewrote the problem, essentially, and I showed all my work, and I drew a box around my final answer. So you should have notes that look very similar to that, okay? Things that I said out loud that you might need to know, you should have written down. Maybe you want to flip back in your notes and find out and list somewhere in your notes the Pythagorean triples. You might need those. They're going to come up a lot. All right. Maybe you want to go back in your notes and write down the Pythagorean identities, the reciprocal and quotient identities, whatever. Get those written down. Things like that you want to add, go nuts, add that. In the meantime, for this, I'm going to ask you to do on your own the following example. Given tan u equals -2 over 3. So now I'm giving you tangent instead of what I gave in the last example, with u between 3 pi over 2 and 2 pi, so then you should know where to draw this. Find the exact value of cosine 2u, all right? You're gonna follow the exact same process that we did earlier and apply that process to this problem, and I wish you all the luck. So if you have to press pause to make sure you write this down, go ahead and do that. And I'm gonna move on to guided example number 2. In guided example number 2, the directions are to verify the identity. We did some verifying of identities in lesson, now I don't remember, 13 maybe? So we went over the fundamental identities, and then after that, we verified a bunch of identities, okay? That is where you have an expression or sum or difference of multiple expressions on the left side of the equal sign, a different thing on the right side. And because it's being stated that this is an identity, that means that this is in fact equal to this. You can't really solve an identity because when you solve something, you're finding what value for the variable will make this equation true. But when it's an identity, it's always true. So really, anything within the domain of those expressions will make it true. So that's like saying, when does this line equal this line? And the two lines are on top of each other. Always. So for all x, or for all input, or for the entire domain, whatever words you want to use. So when we were asked to verify something, you're really just being asked, can you change one side of your equal sign and show me how this does in fact equal this, using anything that we have already established as being fact. So in order to do this particular identity, and what you'll do in the next example for on your own, is I'm going to pick a side to change. Now, normally, I always told you guys to pick the busier side because it's easier to take something busy and simplify it rather than take something simple and make it more complicated. However, here is an exception. Here I have cosine of 3x. Now, that's not quite a double angle, it's a triple angle. We don't have an identity for that, but we're going to build our own. I'm going to use this side since the section we're on, use context clues, guys, critical thinking. The section we're on is all about this double angle identity. So what I'll do is, like I said, I'm going to throw back, and I'm going to also tie in angle sum identity. So I hope you have those handy. If you don't, press pause right now, go find your angle sum and difference identities from lesson, now I don't know what number we're on, 19, and this is 20, can I count? And get those, all right? So I hope you have those handy. The first thing, so I'm going to change the left until it equals the right. The first thing I'm going to do for an example like this one is I'm going to rewrite 3x as a sum. So I'm going to use x and 2x because I have an identity that I can use if 2x is involved, and regular x is fine because everything here is already regular x, right? Plain 1x. Then in the next step, I'm going to use x, treat that as my alpha, and then 2x, I'm going to treat that as my beta. So I'm finding the cosine of alpha plus beta. That formula or identity that we did is cosine alpha, cosine beta. Now, looking carefully at what you wrote, we wrote plus minus inside this, and then on the other side, we wrote minus plus. So that means that when this is plus, this is minus sine alpha and sine beta. Since alpha is x and beta is 2x, I'm going to fill that in next. That gives me cosine x cosine 2x minus sine x sine 2x. Now remember, my goal is on the right side to have everything is just an x. So cosine x, you're cool, and sine x, you're cool. You guys are not cool. So I need to do some work with them. So in this current lesson, lesson 20, sine of 2x only is equal to one thing. Cosine of 2x, we have three options. When in doubt, I kind of default to the first option. But, we'll cross that bridge when we get to it. I'm just going to start with this one since I only have one option. So that means I have sine x, which is the one above it, times this. If you look at your notes, lesson intro for lesson 20 is 2 sine x cosine x. Now, before I really finally decide what I'm going to fill in there, I'm going to clean that up a little. 2 sine times sine is sine squared. So 2 sine squared x cosine x. So this looks pretty good, except I have a 2 in front for that double angle identity. And that has a 3. So we're going to have to figure out what is going on with that. But we'll get there. Now, I'm going to, there seems to be like no sure way to figure this one out, like what we should fill in. So I like to pick that first one because then I could always manipulate that if necessary. Cosine x times, that means I'm going to have cosine squared x minus sine squared x. That was the first of the three options. What I'll do next is I'm going to distribute cosine into my parentheses very carefully here. Cosine times cosine squared, well, that looks pretty good. I'm on the right track. I'm going to get cosine cubed. Minus, well, now that one has sine squared in front and then cosine. So this, I normally, I guess in the next step would write cosine x sine squared x, but I'm going to use commutative property, turn it around. I'll just write sine squared x first, cosine x. Now this is good because minus this really has a -1 in front. These are actually like terms, believe it or not. So that's really got an invisible -1 in front. They're both sine squared, cosine, sine squared, cosine. Combine like terms. What are we left with? Cosine, sorry, that's a 3. Cosine cubed x minus 3 sine squared x cosine x equals cosine cubed x minus 3 sine squared x cosine x. So every step of the way, this was just like a little extra inserted showing my work kind of step. So I'm just going to put little stars by these, just showing some work. So that I did next, and then that just carries down. Okay, so I hope you understood this, and then I'm just going to put a little check, verified. There we go. Okay, so again, from the top, I have a 3x. There's no triple angle identity. Now, could you write this down as one possibility for a triple angle identity if you wanted to make your own list? Sure, but most people don't because it's just one more thing to memorize. It's not quite necessary. It doesn't come up often enough. It's not really worth it. But if you're a superstar at memorizing stuff, go crazy. But there's going to be more than one option for this, especially due to the fact that cosine of 2x is involved. All right, so I will kind of circle off my final step, but really for an identity, it's not just about, and like most of these problems, but especially on identities, when we verify, it's not just about the final answer. You already know what it should equal. That's not what I'm looking for the last step. I'm looking for the work. I'm looking for the process. I'm looking for you being able to show how to get from point A to point B. And that's what it's all about. So make sure you show all your work. Okay. So I'm going to show you on your own example number 2. Similar concept, except in this one, instead of using cosine, we're going to use sine. You will still run into the same obstacle. Cosine 2x will pop up, I promise, in the problem if you're doing it correctly. And you're going to have to make a decision. Since I only have sine on the right side, that's going to help me make my decision on as to which of the 3 cosine double angle identities I'm going to use. If you need to press pause to finish copying this down and to work on it, go ahead and do that. And then when you're done, you're going to pick up at the guided example number 3. And actually, if you guys remember, whoever's watching, to make maybe timestamps in a comment on the bottom for me. So say like, oh, on your own example, or rather the guided example. So guided example number 1 starts at this time. Guided example number 2 starts at this time. Guided example number 3. And then I'll put that in the description underneath so that you guys could jump quickly, or if you guys could search the comments if someone else already put it. So if you go off, work on this, and you come back to the video, it'll be easier to jump, to the next example. Hopefully that makes sense. Let's work on guided example number 3. Solve tan 2x, or tangent, plus tangent x equals 0 for x is between 0 and 2 pi. So x has to be an angle between 0 and 2 pi, 1 full revolution on the unit circle in a way. Whenever it says exact value in the directions, it will probably mean you don't need a calculator. In this case, I'm just giving you the heads up, you don't, okay? It could be an exact value directions kind of question. If it says approximate value, that indicates you'll need a calculator because you're going to round. Always, always remember that. Now, I do like that this guided example is already equal to 0. That's great because if it's equal to 0, that's usually a good sign. Get it? Because it's a little easier to take it from there. You need to remember that solving should be synonymous with factoring. I don't think that people think about that enough. They just focus on isolate x, get x alone, get x alone. But really, in order to do that, factoring is often involved. And You want to take out a greatest common factor. You want to factor using a C method or grouping or sum and difference of cubes or difference of squares, whatever it may be. You're probably going to factor, but we don't have a GCF right now because the angles aren't the same. One angle is 2x and the other angle is x. In order to do the factoring that we might need to do, I need for this to not be a double angle. I need it to just be an angle like x, or I need to somehow double that. But it's much easier to use our double angle identity, rewrite this, clean this up, and go. So all you're going to do is you're going to rewrite tan 2x as the double angle identity for tangent, and you won't have 2x anymore. It'll be just tan x everywhere. Okay, you should find that lesson intro for lesson 20. This is going to equal then 2 tan x, you want to work on memorizing these, over 1 minus tan squared x, that's just the double angle identity, plus tan x equals 0. Now I left an awful lot of room here, and that's because I like that it's already equal to 0. I don't want to start bringing things to the other side. So I want to bring these two things together. This is going to kind of be reminiscent of when we did verifying identities or simplifying expressions. So I want to bring this together and group it all up. So I'm going to find a common denominator. In order to find a common denominator, I'm going to multiply both my numerator and denominator, which is an invisible 1 right now, by 1 minus tan squared x on top and on bottom. Now, sometimes that's not the best thing to do, and sometimes it is, but we're going to get there, baby steps. We're going to do one thing at a time here. Now, next step, I'm just going to rewrite this all over 1 minus tan squared x. Do not multiply that over to the 0. You will be more or less throwing away answers, so we don't want to do that. You may also want to keep in mind that we might have extraneous solutions because your denominator can't equal 0. So if tangent x equals either 1 or -1, I'm going to square it and get 1. 1 minus 1 will be 0. When does tangent equal 1 or -1? At the pi over 4s. 1, 3, 5, and 7 pi over 4. So if any of those pop up, throw them out. They're extraneous. You're welcome. Now here, I have a lot of room, so I might do 2 steps in one. I shouldn't really do that, but here I'm going to start off with 2 tan x plus, then this is really tan x times 1 minus tan squared x, like that. You have options. Some of you are going to be instinctively inclined to just distribute that tangent. That'll give you 2 tan plus 1 tan minus tan cubed. 2 tan and 1 tan you could combine like terms and get 3 tan. And then you'll have 3 tan x minus tan cubed x, and you could factor out a tangent, right? And then pull that out front. If that's what you want to do, why don't you press pause and go ahead and do that. I'm just going to show you a different spin on things. This is one piece, and this is another piece right there. I'm going to factor out my greatest common factor of tan x now. If I do, just an option, tan x out front, then what's left here? Just a 2. What's left here? Really just 1. Not 0, but 1. And 1 times that, well, I guess I don't need those parentheses anymore. So plus, fortunately, if it were minus, I would have to distribute again, but plus 1 minus tan squared x. If that is a little weird to you, press pause, go back to what I said to do in the first place, do it that way, and just see if you get the same answer as me, okay? You got this. Don't panic. 2 plus 1 is 3. So I have tan x, and then remember, these are being multiplied. These are factors. 2 plus 1 is 3 minus tan squared x. Okay. In order for any fraction, so really, what am I working with right now? I'm just going to grab a highlighter. I know I have 3 steps here, but my left side of the equal sign is this, underneath this salmon colored highlighter, equals 0. Now, important concept all the way through to calculus, but a fraction, rational expression, something that has a numerator and denominator, and we have functions on both. This equals 0 when the numerator equals 0. Okay, a rational expression, a fraction, equals 0 when the numerator equals 0. So 0 over 1, remember, that's okay. That equals 0, right? But something over 0, no. That equals undefined. So if I want to know when does this fraction equal 0, I'm really concerned with when the numerator equals 0. And I'm already factored, so I'm just going to go ahead and continue with that. So tan x equals 0. I'm going to solve that. And 3 tan squared, 3 minus tan squared x, sorry, a little squished, equals 0. Here, you might choose to rewrite it using trig inverse, or just ask yourself the question, tan of what angle or angles equals 0? You might have to go back again. Another reference to an old lesson, tan, the meditating man. So if you need to go look at that, go and look at that. But the tan of what angles equals 0? You should get when x equals 0 and when x equals pi. Yes, 2 pi is also normally an answer, but this asks me to solve when x is less than 2 pi and not equal to. So that's 2 answers right there. Tan, meditating man, remember zeros on the sides. Next, here we go. 3 minus tan squared x equals 0. I'm actually going to add the tan squared x to the other side because I don't like negatives floating around when I don't need them. So 3 equals tan squared x. Remember, I just added tan squared to both sides. Now I'm going to take the square root of both sides. When you're the one taking the square root of both sides, you have to put plus minus out front. So plus minus root 3 equals tan x. Again, I took the square root of both sides. I had something here, right? Took the square root. Now I'm asking myself the same type of question. The tan of what angle or angles, the tan of what angle or angles equal square root 3. Go back again. Tan, meditating man. He was so wise, right? He was very wise. Root 3, he associated with certain angles. And then root 3 over 3 with certain angles. And then he knew when they were positive and negative. This is kind of even easier because we want plus minus, so we just want all of the answers between 0 and 2 pi. That's great. What are those answers? X equals all the pi over 3's. So that's 1 pi over 3, 2 pi over 3, quadrant 1, quadrant 2. 3 pi over 3 is pi, but on the bottom there, 4 pi over 3, quadrant 3. And 5 pi over 3. That's on quadrant 4. So I just found 1, 2, 3, 4, 5, 6 answers. So I just found 6 answers to this problem. Like I said, this 1 minus tan squared x is not allowed to equal 0. When will it equal 0? I'm just going to keep going. Add tan squared to both sides. I did that out loud before. I'm going to show it here. So you're not solving when does it equal 0. We're just solving when does it not equal 0. So we know what values x is not allowed to be. Square root again. So we get plus minus square root of 1 is 1 equals tan x, because the square root of something squared is just the radicand or the thing on the inside. And then tan of what angle or angles between 0 and 2 pi, of course, are equal to 1. And those angles were, not equal. X cannot equal then pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. But none of those answers came up, so I didn't have to make anything extraneous anyway. So I'm just going to go here. I'm going to label this restrictions. These don't come up all the time, but you want to keep your eyes peeled. Always keep that in mind, because you don't want to do all this work, find these answers, and then realize, oh my gosh, that can't be. I mean, that's such an analogy for things in life anyway, right? Like, you're shopping for a new sofa and you love this sofa and you think it's great and you want to buy it, and then the delivery people come and it can't fit up the stairs and you don't have any other way to get it inside. You didn't think about your restrictions. You have to think about those things, okay? That's the end of guided example 3. I hope that there's timestamps on the bottom if you need them for later. But on your own, I picked an easier one. I chose to do the harder one with you, the more challenging one with you. And on your own, you're going to solve this one. Solve sine 2x cosine x equals sine x. Remember, I talked about that happy zero. We are going to want everything on one side. Remember, you can't combine things unless they're all x or they're all 2x, okay? And this is the double angle identity section. You're probably going to have to use the double angle identity. Factoring should be synonymous with solving, things like that. We're going between 0 and 2 pi. And this one, you should be able to have no problem finding exact answers. You don't need a calculator, okay? If you have to press pause, go ahead and do that. But honors students, yes, honors students have an additional problem. For honors, you're also going to solve this one. So 1 minus 3 tan squared, I'm sorry, not squared. Be careful how you write this because some of you are a little messy and your 2's might start floating and then they become squares, right? That happens a lot when you guys copy homework from each other because you can't read each other's handwriting, and usually I figure out who you copied from because I could tell who writes their 2's and whatnot a certain way. So don't do that. But here you go. That's for the honor students only. Press pause if you need. And I'm going to move on to guided example number 4. Guided example 4, find the exact values of sine 2x, cosine 2x, and tan 2x, given that the tan of x equals 2 and x is between 0 and pi over 2. All right, I know I need to find these. I'm going to have to use the identities. I will write those down in a moment, but I want to draw my picture. Yeah, I'm going to draw my picture first. Tan of the angle x, which is between 0 and pi over 2, quadrant uno, is equal to 2. Please remember that means 2 over 1, and that's your opposite, and that's your adjacent. Quadrant 1, sketcheroo. Reference triangle, reference angle, opposite, adjacent, not a Pythagorean triple, so I'm going to use Pythagorean theorem. 1 squared plus 2 squared equals c squared. 1 and 4, 5. So c equals root 5, and the hypotenuse is never, ever going to be negative. Then we have, I don't know why I was drawing another picture. That was silly. What we'll do is we're just going to use this information to find our double angles. Now, what I might write down though is what does sine x equal, cosine x, and tan x? Just get those written and out of the way because I'm going to need them in my identities for double angle. Sine is opposite over hypotenuse, 2 over root 5. Now, if I were squaring that, I could leave it, but I'm going to rationalize because the radical will go away. That's going to end up being 2 root 5 over 5. Cosine, adjacent over hypotenuse. Again, rationalize. That's just going to be root 5 over 5. And tan is opposite over adjacent, or 2. So I'm just going to circle that because I'm going to reference those momentarily. So let's do the first one. Let's call that A. Sine 2x is equal to 2 sine x cosine x, which equals 2 sine x we just found. Now, watch what happens when I don't use the rationalized answer, 2 over root 5. Cosine is 1 over root 5. Always think ahead, okay? 2 is 2 over 1, so 2 times 1 is 4. 1 times square root 5 times square root 5. Square root 5 times square root 5 is square root 25, which is 5. Well, there we have it, 4 over 5. Nothing to rationalize and nothing to simplify. Oops. Part B is cosine 2x, and I can use cosine squared x. Oh, I should have written, I'm sorry, cosine 2x equals minus sine squared x. So equals cosine squared minus sine squared. Again, look what happens when I use the one that isn't rationalized. Just careful we go in the right order. So that's 1 over root 5, and that's 2 over root 5. Think ahead. Don't do something unless, it seems like a good idea. Squared. Okay. If we want to square, 1 squared is 1. Root 5 squared is 5. Minus 2 squared is 4. Root 5 squared is 5. 1 over 5 minus 4 over 5 is negative 3 over 5. There we have it. Cosine 2x equals -3/5. I should have circled those. Now, when we do part C, guys, as a trick, I'm just going to do this because I already have them. Oops. Then that would equal 4/5 over -3/5. Then keep change flips, so tan 2x equals 4/5 times 5/3. Do not multiply those, the 5's reduce. So tan of 2x equals 4/3, but I'm going to write it as -4/3. And there you go. Guided example number 4 is done. And here is on your own number 4. I'm going to end this video here. We have 2 more guided examples and on your own examples, but I just think that this is enough for one video. So I hope that you're able to find success on these examples. Read carefully and make sure you get help from me or someone else if you need it to do any of these on your own examples. And I wish you all the luck. If you feel pretty confident about how you've done so far, thumbs up for yourself, thumbs down for me if you don't feel good. All right. If you feel like I don't know what I'm doing, put a thumbs down. All right. And I will maybe modify how the next 2 examples are if you aren't feeling good. So if we're feeling okay, I'll keep it the way I have it. If you're not feeling okay, maybe I'll, throw in a couple extra practice of ones like this into the guided. All right. Have a great day.